All right, guys, today we're going to be talking about 5.1b, polynomial functions end behavior. I can determine the end behavior of a polynomial function by its degree, sign of the leading coefficient. So we're talking about end behavior of a polynomial function. And here we're kind of telling you how you're going to be able to figure that out. It's by its degree and by the sign of the leading coefficient. Okay, so I've got this little table here down below, and we're going to talk about that in a little bit more detail here in just a second. But in order for you to really try to understand what this table is really saying, I think we actually need to go look at some graphs and then come back to that. So I'm going to go ahead and switch over to Desmos here real quick, and we're just going to go through a couple of different graphs. Let's see. Let's start with y equals x plus 2. Pretty standard linear graph. Again, you kind of understand why it would be called a linear graph, because it's just a straight line. And obviously there is no turns in this particular graph. There's no bends, no turns. It's just a straight line. Again, the reason it's called a linear graph. I want you to think about the fact that that x is raised to the first power, okay? So if something's raised to the first power, again, just think about the fact that it's linear, that there's really no turns to speak of, and it's kind of where we are, okay? All right, so let me move this guy out of the way because we're going to need it out of the way. Let me go ahead and I'm going to delete this one. Go ahead and do another one here. So y equals x squared this time. Let's bring up this menu so we can see what we're doing. X squared minus 1. And here this time you see that there is actually a turn in this one, okay? There is, in fact, a turn in this one. And that's because here, notice we have this is squared now. It's no longer linear, it's quadratic. But I want you to notice about how many turns it has. Basically has one turn, right? And so we're moving from the left to the right, and you notice that there is only this one turn in the graph, and then it turns back uphill again, okay? I also want you to notice your end behavior. Now, again, if we were just to zoom this out a little bit, you can see here that this just keeps going on and on and on and on forever. But what I want you to see is that this end point is pointed up, and this end point is pointed up, okay? So both of those are pointed up, and there is only one turn in this graph, okay? Let me just show you, what if I change this to a negative x squared, and you notice what happens. All of a sudden, there is still just one turn in the graph, but I want you to see that now my end behavior has changed. Now my ends, if I were describing those ends to somebody, I would say, well, I have one end that is down and the other end is down as well, okay, just by changing this negative sign right here. Well, let's look at what happens when we take this on up another level. Again, both of these graphs we've kind of seen before, but now we're moving into new territory for us. And so let's graph another one here, and we'll do y equals x to the third this time. It's already looking different than what we've seen before. Plus 2x minus 1, okay? I don't know if I like that real well or not. It doesn't quite do what I want it to. I tell you what, I'm going to do a little bit differently here. I know I'm switching things up. It's okay. You do 3x minus, yeah, that looks a lot better. All right, so now let's look at this graph, and I'm gonna go zoom in here tight, close, so that you can see. And again, we're looking at two things. We're looking at end behavior, and we're also looking at how many turns this graph has. Okay, so again, end behavior, maybe not something real exciting, but you can see on this left-hand side, I'm pointing up, and the right-hand side is pointing down. Okay, so it's totally different behavior than, say, something that was squared, because when I had something that was squared, it was either both pointed up or both pointed down. And then here I want you to notice something else. Again, I've got something here that's to the third, and you will note that I have one turn and two turns this time. Again, just by way of memory, let's just do y equals x squared one more time. And you will note here that this one only had one term. Well, now all of a sudden, when I go to something that is to the third power, I have two terms. What do you think is going to happen when we do something with to the fourth power? Let me go ahead and erase out those. And let's do this. Let's do x to the fourth power this time, minus 2x squared plus 0.5. Oh my goodness gracious. Okay, again, now all of a sudden we have got something crazy going on here. Notice again in behavior, what's happening here is I'm actually going up and up. This sounds almost like the y equals x squared graph, right? I mean, we had the same type of scenario, up and up or down and down, right? Except this time, look how many turns I have. Remember, my degree is always determined by my highest degree exponent. So my highest degree exponent is x to the fourth. So look at how many turns I have. I have one turn here, I have a second turn here, and I have a third turn here. Hopefully you're starting to see kind of a pattern here between these graphs, as well as maybe you're maybe a little bit freaked out about what's really happening with this in behavior here. So let's go back and let's look at our notes again, and let's just see if we might could figure this out, okay? So what I want you to notice is it says in behavior of a polynomial function of degree n with leading term axn moving away from the origin. All right, so I want you to think about this. Y equals ax to the n. And I want to add one little caveat here that they did not put on this particular little graph. And I'm going to say where n is greater than 1, okay? So what I want you to notice here about in behavior is when we're talking about in behavior is this a term right here. Remember when we had y equals x squared, for example, we had a graph that kind of looks like this, right? And so you realize that there is a 1 here, but that 1 in fact is positive, okay? So I do have a positive 1 right here. And so that is part of this a term here. Actually, let me make that a different color just so that makes sense. So this is kind of my a here. And then you will note as well that this n is my exponent. And you notice my exponent here is a 2. So you notice when this is positive, for example, and this number here is an even number, notice what happens to the end behavior of my graph. Notice what happens to the ends of my graph. They go up and up. Now look at this table that we have here. This table is basically split up into saying, okay, here's a positive and here's a negative, and here's n even and n odd. So again, if you notice here, my a term was positive, makes sense, and I had an even exponent. So notice what it says my n behavior should have been, up and up. And as a matter of fact, that's exactly what I had. Okay, now let's think about this again in terms of what if I have y equals negative x squared. Okay, in this case, I still have the 1 here, but notice now instead of a positive, I actually have a negative. And notice here that I do still have an exponent that is even. Okay, but let's think about what the graph of this does. Well, the graph of this actually turns down and down, okay? So this time we have down and down based on what we have here. And again, we go right back to the table and look, our a term here was a negative 1. And so it was negative. And you notice again that it was even, an even exponent. So it went down and down, okay? All right, so let's look at this just a little bit further, and we'll see these other examples come to pass, okay? So notice, let's go back to our graph real quick. Notice I have x to the fourth minus 2x squared plus 0.5. All right, and really all I'm really looking at is this leading term. I'm looking at my leading coefficient. Now, obviously, it has to be written in standard form in order for you to be able to use that. But I want to just note here what my leading coefficient is. My leading coefficient on this one is x to the fourth, okay? So let's think about it again. I have a 1 right here, which is my a portion. Okay, this 1 is my a portion. And then again, this n is the fourth degree. Okay, it is an even number. Okay, so because it's an even number, notice what my end behavior is. I have positive and I have even, so it is up and up. Okay, and notice, look at my graph again. Up and up is exactly what's happening here. Okay, now conversely, if I were to have a situation where, for example, I had y equals 6x to the third, okay? 6x to the third. Well, what I want you to see is, again, I'm just looking at this a term right here, and I'm looking at my n term right here. Notice this is positive. Okay, should have put that in blue. That is positive. And notice here, though, that this is odd. 3 is an odd number. 1, 3, 5, 7, all those are odd numbers. And so notice that I have a positive a value, but I have an odd exponent that it's being raised to. So what I can determine from this is that I'm going to have a graph that is going to be down and up, okay? Not sure exactly what that's going to look like, but we'll just kind of draw this out just a little bit. So maybe it would look something like that, okay? So I would have one endpoint that's pointed down and one endpoint that's pointed up. Conversely, if I were to take y equals negative 4x to the third, notice again, my a term is a negative 4. This time it is negative. And as well, I have an exponent that is odd. Okay, so if I have negative and odd, again, just kind of like almost like matching up multiplication tables, for example. So if I take my negative and my odd, they intersect right here in this particular spot, which means that this is going to be up and down. Okay, so again, if I were looking at this particular graph, then I would understand that I would have up and down. So maybe it would look like this. It's kind of like the reverse of what we had over here. This one would be up and this one would be down. Okay. So quite literally, you can take any kind of polynomial that you're given, as long as it's written in standard form, and you can figure out what the end behavior of that particular graph would be. Okay. So let's practice one here real quick, and we'll just kind of go from here. And I'll leave the table kind of up here so we can see. So let's just do this example. What if we had y equals 3x squared plus 9 minus x to the third? Now, the first question I'm going to ask you every single time, and it's the question you should ask yourself, is this written in standard form? Because if it's not written in standard form, it is going to be really easy for you to just think, okay, well, this is my leading coefficient. But really it's not, okay, because this is not written in standard form. So one of the first things we need to do is write this in standard form, which means we're going to take our highest exponent first. So it'd be negative x to the third, okay, plus 3x squared. And so you see that we're going in descending order, plus 9. Okay, now I have this written in standard form, and now I can really look at my leading coefficient. So if you notice here, I have negative x to the third. Remember that there's always a 1 right there. So you will note that I have a negative a term, and I have an odd exponent, okay? So again, going to our table, negative and odd, that means this graph is going to be up and down, okay? So that's actually what you would have for your answer. You would just choose the answer. These are going to be multiple choice. So you're just going to choose the answer that would be up and down. Now, how could I check that to make sure that that is correct? Well, obviously, I could go to Desmos and I could go ahead and put in that particular graph, negative x to the third plus 3x squared plus 9. And you may have to zoom it out. That's okay. Notice what happens when I zoom it out. This end is up and this end is down, which is exactly what we had as our answer, okay? Pretty doggone simple, not very hard at all. The only other thing you're going to be asked to do is you're going to be asked, actually, we're going to give you a couple of graphs, and you're going to have to figure out what degree that those graphs are. So let's just practice one of those examples real quick. So for example, if you had a graph that kind of looked like this, let's see. Just going to kind of make one up off the cuff here. Okay, so again, let's just think about the sign of the leading coefficient and the degree of the function. Well, let's look at how many turns this thing has. Okay, first of all, so you notice I have one turn right here and I have one turn right here. So I have two turns. Now let's just think about this for just a second. If we had a graph that looked like this, okay, it only has one turn, but you know that this particular graph is actually y equals x squared. Okay, so you have a degree of 2, but yet there's only one turn. So there's always one less turn than there is the degree of the function, right? This is a degree of 2. It has one turn. So if this one has 2 turns, then what can we say about its degree? It has to have one more degree than it has turns, okay? So this one would be third degree, okay? Now let's just look at this end behavior. You got up and down. So what can we say about the leading coefficient? Again, this table is going to be pretty important, okay? We've got up and down, and we've got an odd degree. So that would mean that our leading term would have to have been negative, okay? So that meant that this would have had to have been negative in order to come up with this particular graph, okay? You are going to have a couple other questions. It's going to be an error analysis question, as well as you're going to be given a table, and you're going to be asked what the degree of that polynomial function is. I'm not going to let too much out of the bag here, but you can actually use Desmos to help you graph anything that even gives you ordered pairs, all right? This is a huge advantage over maybe the TI Inspire in that you can actually go to Desmos, and let's say you wanted to graph something and you were given a table, for example, you can actually input a table. If you go right over here to this plus icon, you can hit table and you can actually put X and Y coordinates in there, okay? So that is going to be very helpful on that last question. Again, this is not real difficult. It's just one of those things that we've never seen before. And so it may be something you need to go over just a little bit. But again, this little table right here, I would encourage you to kind of jot this down in your notes. It wouldn't take you very long just to copy this little table down. And that way you can look at any leading coefficient as long as you've got it in standard form and tell what the end behavior of that graph is going to be. Okay, so hopefully this has been helpful. If you need extra help, make sure to just reach out to us and we'd be glad to help you with anything you need help with. Thanks.